Anyway, well, I'm glad you're here. So what I had is, here's my original plan. My original plan was that I thought we might get a little further along on our, having people come up and do the problems on the board. And then I thought we might finish that. And then this was last week I was thinking about. And then I was going to give it like a little quiz, like the second half of the period, the first half of the period, maybe tomorrow. And then I was going to give a test on Thursday. And I thought that would work. But I don't know, the more I thought about it, number one, Wednesday, you actually don't have this class. Wednesday, you have career day, all right? So last week when I wasn't thinking as well, I guess, I didn't even think about the career day. I just thought, all right, quiz, and then I still have Wednesday. It's just not going to work out as well as I'd like to. So here's what I would like to do. I'd like to propose the following schedule. All right, today I might have a group come up and do one of the isotope problems. I might do that, and then what I want to do is I want to stop having the group presentations on that, and I will do this today, percent composition, and also get into empirical formula. Okay, then no quiz tomorrow. Okay, and what I would do is review this and do empirical formula, and then do molecular formula from empirical, which takes about 5 minutes. That's about a 5-minute lesson. And then also I want to review stoichiometry with a limiting reactant. So we'll go back to the homework questions and probably do the stoichiometry on that. Okay, so then what happens is I had another person in this class ask me, because and I did see that you had an AP calculus test last week when I had to do this. I saw that. I just said, well, you can have 2 tests in a day, and I agree. Yeah, but that's 2 tests. That's 2 big tests. So I'm not going to give up completely doing it. But what I did is I would like to give a smaller version. It's a quiz on Thursday instead of a test. And I'll even tell you what it looks like. There are 11 problems like the ones in the homework. Okay, they're like the ones in the homework. And this one you have to show your work. Okay, yeah, that's the difference between this one. You do have to show your work. So if I say to do an isotope problem, you just have to show your work. There'll be 11 of those problems on there. You can choose 10, and there's 6 points apiece. I give 4 points for the work, and I give 2 points for the answer. Now that should soften it up a little bit on Thursday. You get that? Some of you will actually finish that. You'll probably finish it maybe within 30 minutes. I'll give you the whole period. So some of it will be done in less than that. So that if you want to even study for your, is the calculus after mine on Thursday?
This Thursday? Yeah.
So I'm going to do that where you still have something you're going to do. And then this is where I had to compromise, and I want you to compromise too. I'm going to take the first 15 minutes next Monday, and I'll go over this quiz. See that? And then also, then I will give you part 1 of the test. I'll also want to take the test and break it up into pieces. So then you would have, for 30 minutes, you would have where you classify and balance equation, and you'll do a stoichiometry problem where you have to, you don't have to show your work. You don't have to show your work. It's just short answer. You get that? The only ones you have to show your work are right here on Thursday. So this will also takes about, many of you will get that done in about 30 minutes. If you want, you'll have more than that. You probably have 40 to 45. And then on Tuesday, you would have part 2 of the test, which is the author's multiple choice questions. And again, you don't have to show your work on those because they're multiple choice. Got that? So what I did is took the quiz away from Tuesday, moved it to here. And then this should be easier to get ready for that. Got that? But then you had to come back, and even on this day, it's classifying and balancing, and you do a stoichiometry problem. You don't have to show your work. You just got that? That makes, I used to do these 2 together on the same day. And so I'm gonna take a little pressure off of you and say, but I am gonna split it up into 2 days. And then this would be strictly the author's part of the test, and that's 40 multiple choice questions. All right, what do you think? It took me a long time to figure this out because I felt like I couldn't give you a quiz here. I wouldn't quite be ready. We need to finish some of this other material. And then, and that would be 3 pretty good grades. There's a 60-point grade there, a 70-point grade, and a 120-point grade there. So I would say that's a nice chunk of work. And I think stoichiometry is one of the most important parts of chemistry. All right, what are your comments? What do you think? I'll have to put this on the calendar. This is not on the calendar now. The only thing that's on there, it says you have a test, but it's actually down to a 30-minute quiz. Yes?
So you said that part 1's going to have one stoichiometry that we're not going to have to show a word for?
Right. It'll be short answer. It'll be like, how many grams of, and you put the answer in there. You don't have to show me how you got it. You just put the answer in there, though, like 3.5 grams.
And then for part 2, are we going to have to do that when we will show word, or is it just...
On this is all multiple choice. There are authors, questions from the book. Now, I picked them. I picked them, but there are 40 multiple choice questions. Now, you still have to have a certain amount of speed. You still have to have a certain amount of speed on this. You know, there are little stoichiometry, shortcuts. You'll be using shortcuts a lot on that one. So that one, that'll take a little pressure off of you. This used to take a little more than an hour. I used to give them a little more than an hour, but I'm going to split it up now, so it's 30, and you can have the whole hour on this one too. So, and I know that you guys, there's a lot of things going on at college too, and I'm trying to listen to some of that, but this should soften it a little bit for this week. I don't know, yes? It should soften it a little bit. And then Monday, it's not super, it's like you classify and balance, and then you do stoichiometry problems. There are 2 of them. You don't have to show your work, you just have to get them right. And I think that a lot of you will finish early enough if you want to even study for calculus or something. You can do that. Yes?
So the homework questions are now due Monday?
Well, I thought I had to be careful about that. If I make them do Tuesday, then you'll wait till the very, very last moment to do them. I don't want to make them do this Thursday, even though that would be the wise thing. If I made them do this Thursday, but then that puts more pressure on you, and I'm trying to take some off. So if I say that the homework are due on Monday, that gives you a whole week from today. When I know you've gotten, originally you thought they were going to be due this Thursday. So I would say Monday, yeah. Is that what I said? I think I wrote it here somewhere. Oh, I put it on Google Classroom. That's right. So, so homework would do on Monday, and then okay, and then what we'll do on Wednesday. This will actually mess the rest of my schedule up, but I'm okay on that. I think it's for you on good. Jeb, you had your hand up. I didn't call on you. Okay, so we'll do peer groups on Wednesday, and then I have to think about this. I have to think about the next week, so I'll think about that. So anyway, that's something you don't need to look at yet. All right. You guys are quiet. Is this good quiet or bad quiet? Yes?
Will there be questions from the reading that we don't go over?
I don't know. That's a good question. To me, if you're doing your homework, you have to look in the book every once in a while. I guess I don't know. I assume you guys are reading the chapter, but I don't. I'm not going to give you a whole test just based on that, but I will tell you the author wrote all those questions. So they have to be similar to probably your homework questions like that. Or all right, we'll see. All right, wait. So this will become a 60-point quiz. This part here, which you could eat this part up. It could be a really good one for you. Get that? That's worth 70. And then last year and the year before, this happened to be the highest part of the test for everybody else. Because the multiple choice, the answer is there, isn't it? It's there somewhere. The only one you have to show your work on, that's the one I'd be ready for. There, get that? All right. But I don't know why it just took me a long time to say what fits with you, what fits with your schedule, what fits with everything else. So I hope this helps you a little bit.
Thanks for being flexible about it.
Yeah, and again, a couple of, at least one person, maybe two, came up to me and told me about some other things going on this week. So now it does, I know that right now it seems great, and then you're not going to like me later because you'll say, wait, I got something on Thursday and I got something on Monday and Tuesday. You're not going to like me then. But this really, I used to do both these on the same day and say, well, I did it right before lunch, I stayed during lunch. So I think this will take a little bit of pressure off of you. Okay, what do you think? All right, so let me get my stuff out here. I want to know who had, I have it written down here somewhere, who had number 6? Everybody, what group had number 6? You had 6? Okay, and all right, so what I'm going to ask you to do is if you'll come up and do that problem. Who had number 7?
I think
You did? It wasn't just you, it would have been your group. Okay, let's do number 6. And I do have, I actually have 3 isotope problems on the quiz on Thursday. It's really very, very similar to this. You get that? All right. Go ahead, I'm ready.
Okay.
You're doing number 6,
I
right?
am, yes.
All right.
Okay, this one, me and my group struggled with for a little bit, but
I like that.
yes, I think we got closest to the answer. Eventually, well, at first, we tried to kind of follow what we did with number 1, like multiplying the abundances.
I got a little harder as you went there, didn't
It did, yes. So eventually, after a bunch of trial and errors, we looked in this packet, which was helpful, very helpful. And it was this part, 3.2b, if anybody needs to look at that. And basically what it talked about was when you have, so the problem looked like this, and if it gives you the isotopes and some of the, it's this one, if it gives you the atomic mass and the abundances, and it's looking for that, you need 2 equations, and then you'll have to do substitution. So this packet said that the first equation was going to be the atomic mass times the relative abundance plus the atomic mass times the relative abundance equals the average atomic mass, which would be on the periodic
you? You
table.
have to remember to look on the periodic table for the answer, right? That's what the mass is supposed to come up with.
So that is what this first equation is. We have 19.99, which was the atomic mass of the neon 20, times X, because X is the abundance, and that's what we're looking for. And then plus 21.99 times Y equals 20.18, which is on the periodic table. So that's the first equation. And then the second equation, this packet
What
says...
did you, sorry.
Yes.
What about your neon, your second isotope?
Yes, that's also where we got a little confused about, because I had done it, before I did it this way, I had done it where I added 20.99 times 0.00257, and I put that in the equation. And then I multiplied that out and subtracted that by 20.18. But when I did it, I got it was farther away from the correct answer than this answer. So I don't know.
All right, so you're using the X and Y, but what did you set that equal to, the one in the periodic table?
Yes.
But doesn't that sounds like it kind of ignores that other isotope.
Yes, that's what I needed to ask you about, because when I didn't with it in it, when I didn't ignore it, I got I don't remember my answer, but it was 93 or something.
Okay.
So
What's
yes.
your final answer, 90?
90.5% of the
Okay.
neon 20, and then 9.5. And I didn't get those when I
Yeah.
added the other one.
Okay, so, any suggestions on this one? I like the fact, as a matter of fact, the X and Y works really well for number 7. The only thing about this one is, if you said X plus Y equals 1, is that what you did? Okay, now, that's the only mistake, because all 3 of them have to equal 1. So X plus Y has to equal 1 minus what? 1 minus the percent of the time that the other one shows up. So, yeah, I know it's a tiny number, but that number is actually 0.0257, isn't it?
Mhm.
If you want to use percent or decimals. So x plus y is not going to equal 1. 1 is 100%, get it? But it's going to equal 1 minus,
Put it
that 0.00257. You get that?
Yes, that makes sense.
And then if you do it, I think it'll come out pretty close.
Okay.
Now, yes,
So do we add the other, isotope, the 20.99, to the first equation?
okay. See, what happens is you can't really set this equal to the atomic number on the periodic table. That's what I'm trying to say. Okay, but I'll tell you what. There's another way of doing this. I keep yours up there, okay?
Okay.
I like the x and y thing, but here's what you could do. What does x and y, let's just say that the first one's x. What does y have to equal? If the first one's x, what does y have to equal? 1 minus 0.0257. Does that make sense? So you could have done this. This is x. This is that number. This is 1 minus 0.00257. And then you'd say this times x plus this times that plus this times 1 minus. And then, yeah, there's a little bit of algebra involved, isn't it? But I think you might want to think about going home and trying that one. Yes?
How would it be 1 minus point like 2.7
Okay. Oh, wait.
with the x?
You know what? I made a mistake. Very good. Excellent. What it should said is this has to equal whatever 1 minus this number is. Take that number. What is it? 0.9? Okay. This has got to be that number, 0.99 minus x. My fault. My fault. One more time.
0.997.
If you take 1 minus this, if you take 1 minus this, then this is x, this is that, and this is that number, that 0.9 minus x. So that 0.999 minus x has to equal the abundance of that one. If this is x abundance, and that's that number, this is that 0.99 minus x. Now, I actually I might use x and y method on the next problem, but on this one, I probably wouldn't. I probably would say something like I just said here. This is x, and this is 0.9. What's that number, Carson? What's it?
Where did that come
0.9
from?
what?
0.99743.
0.997?
Are you taking
Okay.
the 1 minus the percentage that we're given?
Yeah, 100% is 1. So isn't it true that x plus 0.999, whatever it is, minus x, plus that equals 1? So I could do that. I could say that. So I could say this times that, plus this times that, plus this times 0.999 minus x equals on the periodic table. And then solve for x. Yes?
Could you write that out?
Yeah.
'Cause
I'm not going to do it today, but what I'll do is, if you want to redo the problem, if
Okay.
you want to, and bring it again, because that would take me just a little bit of while, and I have to get to some other things today. But now, look at the bottom one. Who has number 7? Do you have number 7? All right, let's do that one. And the one thing you're going to tend to forget is when you say the isotope's mass times the percent plus the isotope's mass plus percent equals what? What is the final answer supposed to be? It's that number in the periodic table, isn't it? That's what you're going to tend to forget. Equals what? Equals the average mass. Okay, ready? This is number 7. Did you use the x and y number? Matt?
Yes. So, for the first one, I added the 4.7 and 3.09% together and then subtracted that from 100 and got 92.21.
I definitely, I like that. You see how she did that?
And then all we were looking for after that was the mass of
Very good.
silicon 29. So then
So-
I just
All right, you added the 4.7 and the 3.9,
mhm,
and you
subtracted that from 100.
subtract from 100. That gave you this.
Yes.
And then you said isotope 27.98 times
Times
point,
the
0.92.
times the abundance, and then I didn't know the.
What's called X?
Mass.
We'll call it X. X
So-
times,
Times the abundance, which is
There you go.
0.04
plus,
plus
29.97 times,
0.0309,
There it
which
is.
is up there.
and then you got that from the periodic table, didn't you? This one's actually, seems a little easier than the other one, once you fill in that number right there. So what'd you get for your answer?
29.01.
All right, what do you think about that? Is that pretty close to the author's answer?
I think so.
It is the author's.
I like these. This is really good thinking. I do have 3 isotope problems out of the 11, and I have the kind of the easy into it, and then you'll probably see one in like number 6 and maybe one like number 7. All right. All right, good job. All right, what I'm gonna do now is I'm gonna go to. Let's just do, okay. Let me just start my lesson if you don't mind. And again, I'm kind of twisting things around a little bit because you guys are not going to be here Wednesday, so I'm going to teach today and tomorrow. And I might even have somebody come up tomorrow and do a couple of problems. Let's do another part of stoichiometry is a thing called percent composition. Now, a lot of books will say mass percent. They use the term mass percent. And what I say is percent composition by mass. Now, I want you to pretend like you're back in the 1800s and you're a chemist. How much stuff do you have available to solve the chemistry problems? You have a balance, probably, and you probably have some chemicals. You could do experiments. But how in the world did they figure this out? How were they able to figure out the law of definite composition, the law of multiple proportion? It was mainly by staying with masses, wasn't it? So what I'm going to do is, let's do a simple one to begin with. Let's talk about this. Find the percent composition of each element in water. So I want to do something, and I know that I'm not trying to waste your time, but I'm going to do the problem twice, 2 different ways, okay? What does this mean? And I know it's Monday morning, don't do that to me. It's Monday morning, but what does it mean, H2O? You say, you want me to say water? No, not really. How much?
So like for each molecule of water, there's 2 hydrogen atoms and 1 oxygen atom.
Okay, we could be in the little world, and that would be 1 molecule of water. Is that correct? That could stand for 1, I'll even draw it for you. We could be in the little world. And if that's the case, whenever you find percent of anything, you always divide by the total. The total. Now, when you're in the 10th grade, I do something like this, and Caleb probably got it right, but Caleb, you have a doubleheader of baseball, okay? And you have the first game, you get 2 hits, and the second game you get 3 hits, okay? And let's say the first game you had 2 hits out of 3 times at bat, and the next time you had 3 hits out of 4 times at bat. And I want to know what your batting percentage is for the doubleheader. Now, so you had actually 5 hits. So, do you divide? You had 5 hits, and you had 2 that you flied out. To find your batting percentage, is it going to be 2 divided by 5 or 5 divided by 2? What do you think?
5 divided by 7.
Oh, what? That's true. So he already knows his lesson, doesn't he? You have to divide by the total. What was the total number of times he batted? 7. You have to divide by the total. And how many hits did he get? See that? And that's how he'd find his batting average for that doubleheader. So same thing here. If you want to find the percent, you always divide by the total. So let's try it. What is the total mass of H2O? In the little world. In the little world. All right, what's the mass of one hydrogen atom in the little world? One what? It's not grams. One AMU. And then the other hydrogen? And what about the oxygen? All right, so what is the mass of one teeny tiny water molecule, 18 AMU? Is that right? Just find the percent mass. Percent mass of hydrogen equals how much of the 18 was provided by hydrogen? 2 out of 18. All right, give me a hit on that. What's this one? And that's 11.1%, right? All right, and let's do a percent by oxygen. I know you can take 100 minus that. You can do that. Or you can do this. 16 of the 18 was due to that. And what is this, 0.888? What do you get? Everybody have a calculator? 0.888, which is 88.9. Now, whenever you're doing this, it should come close to 100. Because of rounding, it might be 99.9, it might be 100.1. But if these don't add up to close to 100, like if you get 97, you made a mistake. Got that? So that's a nice way to just check it out. So every time, if we went down to a little tiny world and I tried to lift one water molecule, I'd say, wow, this is kind of heavy. Well, it's because of oxygen, isn't it? Well, now, let's go into the, what else could this mean? It could mean one molecule of water. What else can it mean? 1 mole. Okay, now 1 mole of water, what's the total mass? Also known as the molar mass. 18 what? Grams. What is the percent composition by hydrogen? Well, if I had a mole of water, I'd have 2 moles of hydrogen atoms. Man, that's a lot of them. I'd have 2 moles of hydrogen atoms. How much would that weigh? Remember that number up here? That number stands for 2 things, doesn't it? Yes?
Yes.
Okay, so what? 2 grams out of 18 grams. What? Whoa, look at this. You know, when I first learned this, no one ever taught this to me really not the right way, I'm sure. Because I'd watch it in one page in the book, they'd be doing some problem with AMUs. I said, oh, okay, I better learn how to do it that way. And I think a lot of stuff I was taught to mimic or to monkey. It's like, this is the way you do it? Okay, I'm going to do it that way. This is the way you do it? That's what I'm going to do. You see that? I could monkey the problems, but I really didn't know exactly what I was talking about. I wasn't thinking about the problems. You get the difference? Same thing here. I would see this in a book where they did an AMU, then I'd turn the page and they were doing something in grams. And I was confused. But yet, I've talked to you about this many times. The mole concept is really big because it reflects, it magnifies what's happening in the little world, isn't it? You get the same answers. So if you read in a book and they're doing it with AMUs, okay, I'm in the little world. If they do it in grams, they're in the mole world, aren't they? In the gram world, aren't they? You get the same answer. So don't tell yourself, I need to do 2 kinds of problems. It's the same problem, isn't it? All right, I'll have you do one real quickly. Now, what I'd like you to do is, these are some of the easier problems, honestly. So I'm going to see if you can do this with a little bit of speed. How about that? You ready? Let's find out what is the percent composition of each element in glucose. And when I say percent, it means by mass. Percent composition by mass. All right, you ready? All right, go. Let's see what you do. Now, if you've been paying attention, you know that I don't care if you want to go into the mole world or grams or or you wanna go in the little world with AM, it's up to you, isn't it? You always divide by the total, isn't that right? Okay, what's on the volleyball agenda this week?
We're playing Calgary tomorrow, which is our senior night. And then I think we play at GDS on Friday.
So just 2 games, and then this next week, is that
Next
regular
week,
season or that?
This is the end of regular season, so next week we'll start state playoffs, and we'll most likely have a double bye
Ooh.
through the first 2 rounds, so we'll play next Saturday.
Oh, that's pretty good.
Oh, we do play when do we play GDS? Oh, then we play GDS Thursday and Washington Friday, cause that, yeah,
Okay, great.
yeah.
I talked to Coach Bo just about half an hour ago or something like that. He said, well, we're looking pretty good. He said, and it's an iffy thing about Sophia, whether she, we'll see, but,
Yeah, we don't know yet.
all right. All right, how we doing? Now, would you raise your hand if you decide to stay in the little world and you used AMUs? Okay. How many of you went into the big world and went to Moles and Grams? And I don't care which one, but a lot of you probably feel comfortable with the Graham idea, don't you? So here we have, you had 6 carbons, and carbons each was 12, isn't it? I actually had 6 moles. If you have 1 mole of glucose, that's 6 moles of carbon atoms. That's a lot of carbon atoms, isn't it? It's enough to make 12 grams. Isn't that right? So 72 grams. And then this is 12 moles of hydrogen. Whew. But each mole of hydrogen has a mass of 1 gram. And this is 6 moles of oxygen atoms, and each of those are 16. I hope that adds 180. Is that 180? Okay, so now carbon says CHO. Carbon says, hey, I provided 72 of the 180. And hydrogen says, well, I provided 12 of the 180. And oxygen says, I provided 96 of the 180. Okay, and let's see. All right, Kyle, what'd you get for the first one?
40% or 0.4 of O2.
What is it in percent though?
40.
Even? 40 point. Okay, I gotta watch your rounding here because
0.02%.
I'll do 40 then. Next one, Kyle, go ahead.
6.7%.
Okay, next one.
53.3.
And we always double check. You add these up and you get 93. That looks pretty good. Again, you don't have to land right on 100 because of rounding, but it should be pretty close. Did everybody get this? Okay. All right. So what I want to do is, I didn't think it would take very long to do percent composition. Are you okay with this? But I want you to think about this. This is what they were doing. Now, they didn't have the mole concept until a little while later, but they were measuring masses and then trying to find percent by mass. But then what? Here's my question for you. I'm going to see if I can find a problem here. Oops. Okay. All right. This is number 85. Problem number 85 in your thing. It says calculate. Oh wait, let's do. Okay, well, wait a minute. Where's the empirical formula? Okay, I'll do 85 anyway. 85 says this thing has 48.8% cadmium, and it is 20.8% carbon, 2.62% hydrogen, and 27.8% oxygen. Okay. Now what they want to know is, they want to know what the formula is for the same. Okay. This is okay. This is cadmium. Okay. So imagine you're back there in 1800s. You got this balance, and you're able to figure out the percent of mass, the percent by mass of each element in a compound. So what you really want to know is, what is this stuff? Is it really CD, C2, H3O7? What is the actual formula? So, and I used to get messed up on here because, again, because I was kind of taught in chemistry at the beginning to mimic or to ape it, monkey it, I thought, man, there's like 12 different kinds of problems that I have to remember how to do. And not only anyone that got to college, here it is again, 12 different kinds of problems. But there were actually with themes. There were themes you could get into, and you don't have to memorize how to do 12 different kinds. Now here's a very typical problem where you send something away to be analyzed. They give you analysis by percent by mass. They'll say, well, what is it? Well, that you have to pay more money if you want that. Okay, so, but eventually I want to know what this is, don't I? So let me show you something. A while ago, when you saw this, I know you don't like me saying this, but what world are you in? And I could be in the little world, the molecular world, right? One molecule, I could. Or I could be in the mole world. But either one of those, when I see a formula, what world are you in when you see a formula? Are you in the gram world? Are you in the mass world when you see a formula? Does this mean like 6 grams of that? And never, never. This is in the world of number of particles. There are 6 of me for every 12 of you, for every 6 of you. And what 4-letter word means you're in the world of number of particles? Mole. So if you understand that, you want me to find you a formula? I can't be in the mass world. This is a mass percent, isn't it? I can't be in the mass world to find a formula. So I've got to get into a mole world, don't I? So here's a neat little trick. Ready? All right, it's 48.8%. Well, how much did you give me? Did you give me a room full, or did you give me a little piece of this chemical? How much of this chemical did you give me? Oh, you're not going to tell me? Well, then I'll pick my own. I hereby declare you gave me exactly 100 grams. What? Can you do that? Yes. You gave me exactly 100 grams. And you know why? Because I'm not dumb. If you give me if you assume a 100 gram sample, you just said it was 48.8%. You didn't tell me how much you gave me, did you? I'm going to assume it's 100 grams. Why would you do that? You know why? Because if it's a 100 gram sample, then how many grams of it have to be cadmium? How many grams have to be? What's 48.8% of 100 grams? 48.8 grams? Yeah, you can do that. Okay. Now, leave a little space here, okay?
We're not using the amount they gave us.
Doing what now?
We're not going to use the molecule where they gave us the problem.
I will. Yeah. So anyway, at least, now I know that 20.8 grams is carbon, and then I know that 2.62 grams is hydrogen, and then I also know that 27.8 grams is oxygen. Do you see what I just did there? Now, I know you guys are so smart, that you're gonna say, hey, if I see that problem, I'm just changing it to grams. Okay, then do it. And some of you, I'll show you how to do it with long cut, but some of you are gonna say, I'm gonna do shortcut, but I'm gonna do long cut first. I have to get into mole world, don't I? How do you get into mole world? Grams of cadmium, moles of cadmium, 1 mole of cadmium. Oops, I don't use cadmium very often.
112.
Yeah, 112.4. Woo. Now, go ahead and what is the shortcut though? Remember this? You're in the gram world. You want to go. You want to go down in the mole world. What do? What's the shortcut? Divide by molar mass. So here we go. Ready? Calculator's ready. 48.8 divided by 112.4. Don't go below 3 sig figs. Sit Lolly, give me a hit on this. 48.8 divided by 112.4.
0.434.
434, and that's moles. Now go ahead. What are we going to do? Shortcut. Ready? Alex, ready? Shortcut. 20.8 divided by the molar mass of carbon.
1.730.
One more time.
1.730.
Okay. Next. Oh, this one's easy. What is this one? Because the molar mass of hydrogen is 1, isn't it? So the shortcut is to divide by molar mass. How about this guy? What are you going to divide by here? All right, what do you got? Gabby, what do you have for this one? Elega. What's 27.8 divided by 16? 1.76? Okay, and that's not grams. Sorry. Moles. 1.7 what?
4.
Okay, thank you. Now, don't go below 3 sig figs. You got that? So let's say you're back in the 1800s and you had to figure this out, and you know eventually you have the mole concept, and you said, I'm eventually going to get into the formula world because I'm in the world of number of particles. Now, this is where some of you are going to get stuck. But here's what we do, right? A lot of scientists were pretty good in math. I will say that. Not all. Not all. Some will even tell you they weren't very good at math. So they went and found a friend of theirs who was good at math. A guy named Edmund Halley. He made some really good observations about this comet. And he read some things about the comet in a book. And he says, I'm not sure how to do the mathematics, but I think maybe that comet that was here 76 years ago, I think that's the same one. What? So he goes to find a friend of his. It had to be Isaac Newton. And he goes through his drawers. And I think I did the calculations on ellipses about 5 years ago. He finds it. He does the mathematics of it. And who gets their name on the comet? Newton's comet? Oh, no. That's how you call it Halley's comet, don't you? Halley's comet. There were people like that in history. Watson and Crick, they weren't as good in chemistry. So they went and found some people that were good in chemistry. Helped them out. So here we have these weird looking numbers. You get that? And this is where you're going to get a little stuck. You said, what is this thing I'm looking for? I'm looking for an empirical formula. I will get to the molecular formula. All right. And we're looking at this thing called the empirical formula. Now, show you real quickly. Could this be an empirical formula? C6H12O6? No, empirical formula is always reduced to the lowest whole number ratio. So this would be the molecular formula, but the empirical formula for glucose would be divide these by 6. Ooh. Now, I didn't say there was such a thing as CH2O, but the empirical formula for glucose is that, isn't it? What if I had another compound, C12H24O12? That's the molecular formula. What's the empirical formula for that compound? Oh, so 2 different chemicals could have the same empirical formula, right? Look at this guy. How about water? That's the molecular formula. What's the empirical formula for water? It is. The molecular could be the empirical, yes.
What's the value of finding the empirical formula?
Okay, I'm getting there. Sorry. Thank you very much. Sometimes, if it's an ionic compound, guess what? remember the two exceptions, peroxide and hydrogen, mercury 1? Except for those guys, when you find the empirical of an ionic compound, you're done. It's already lowest Holman ratio, right? So let's take a look at this one. And so this is where you get stuck a little bit. And this is where mathematics comes in. You remember a long time ago, this guy named Gregor Mendel? Remember he did peas? I'm looking at your eyes. I'm sure in genetics, did they talk about Mendel and peas and tall pea plants and short? I keep looking at your faces. I thought everybody would be going like this by now. Okay. And you see these things. Who this thing? He had a famous 3-to-1 tall to short ratio. Oh, and just like me, when I was in the 9th or 10th grade, whatever it was, I thought, oh, I see. He got 4 plants, and 3 were tall and 1 was short. Really? You're going to make a great scientific discovery, and you only have 4 plants? Really? No. You take stats, don't you? No. He had hundreds of plants. And he had these weird numbers. And a great mathematician says, how do I take ugly looking numbers and tame them into simple ratios? And here's the trick. Ready? Take the smallest number you have here. What's the smallest number of the 4? And divide everybody by the smallest. And let's see what happens.
Not 0.434.
Whoa. Oh, man, I'm sorry. Whoa. Are you sure that's right, isn't it?
Yeah.
Okay. I'll bet you're going to get 1 here. Okay, now give me a hit on this one. Let's go. Calvin, do you have a hit on the second one? What's 1.73 divided by 0.434?
3.99.
All right, next one. Am I going too fast? 2.62 divided by 0.434. How much? 6? And I'll bet the last one is almost identical to that one, isn't it? Aren't these almost identical? Is that right? Okay. Now, when you're doing an empirical formula, 3.99 is 4. 4.01 is 4. 4.3 is not 4. You get it? 4.5 is not 5. But in this case, they actually are whole numbers, and we actually have tamed this thing. Why did I put a 3 there? I'm done. I'll tell you what it is. Here's the whatever this stuff is. I don't know what this stuff is, but it's cadmium. For every 1 cadmium, how many carbons are there? 4. How many hydrogens? And how many oxygens? Now, at this point, I'm a lot further into the chemical. What this chemical is. This is the empirical formula for the chemical. And in the last 3 minutes, let me show you how to do this. Can somebody add this up for me, please? Can somebody add up, I'm sorry, I need to add up all these masses. Well, I need some help here. Wow, that's fast. How much? 230? So you had 1 of those and 4 of those and 6 of those and 4 of those. Man, you're fast. Okay. So let's say that the empirical formula has a mass of 230. Okay. Now, EJ, you had a great probing, great insightful question. Why am I doing this? Sometimes the empirical formula is the chemical, like if it's ionic. This one I have a tendency to think there's something wrong here. It's a mix of metal and this right here. It could be ionic. But let's pretend for a minute that we do another experiment and we find out that the molar mass is 230. What if the molar mass was 230? You'll say, ding, 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 ding. That's the chemical. That is the formula. But what if the molar mass was 460? What if the molar mass of the real chemical was 460? 460 divided by the empirical mass. See that? The empirical mass. This right here adds up to 230, but the real chemical weighs 460. Oh, you can't be the real chemical then. But how many times will this go into that? So what we're going to put down? We're going to double everything, right? Yeah, that's pretty easy, wasn't it?
Can you say that one more time?
One more time. One experiment showed me that the empirical formula was this, but the empirical formula has a mass of 230. Another experiment was done, found out that the molar mass was 460. This can't be the real chemical because the real chemical weighs 460, but how many times will 230 go into 460? Twice. So if we were to double all these things in the empirical formula, if you add that up right here, you'll get 460. Okay, now, you did a good job today. One more time. We will have, it will only take me a little bit of time. We'll review this tomorrow. And then I'll show you one more way to do empirical and molecular formulas. And then we'll probably have some people come up and present some problems. And then I think that'll make it ready for the other thing. And then we'll see, Wednesday will be career day. They'll have that in here. And then Thursday, the quiz.